In 2019, humanity saw something it was never supposed to see: a black hole. Not an artist's painting, not a computer fantasy, not a symbol from science fiction. A real shadow carved into glowing light, sitting at the center of a galaxy millions of light years away. At first, the image looked almost disappointing: a blurry orange ring, a dark center. Something like a burning donut in deep space. But Einstein would not have looked at that image as a blurry picture. He would have seen a test of reality itself, because that darkness in the middle was not ordinary darkness. It was not empty space. It was not a surface. It was a region where light had tried to escape and failed, and the glowing ring around it was not simply fire. It was matter moving near the speed of light, twisted by gravity so extreme that space and time themselves were bent into a lens. So the real question is not, why is the first black hole image blurry? The real question is far stranger. What are we actually seeing? Are we seeing the event horizon? Are we seeing the accretion disk? Are we seeing the path of light bent around the back of the black hole? Or are we seeing the shape of Einstein's theory projected onto the sky? To answer that, we have to travel toward the image, not as photographers, but as witnesses. And we begin with a question Einstein forced the universe to answer. What happens to light when gravity becomes almost impossible to escape? Part 1. A black hole cannot be photographed in the normal sense. If you take a picture of the moon, sunlight reflects from its surface and reaches your camera. If you photograph a star, the star produces its own light, but a black hole does neither. It has no bright surface. It does not reflect light from inside its boundary. Anything that crosses that boundary can no longer send a signal back to the outside universe. That boundary is called the event horizon. It is not a wall. It is not a shell made of matter. It is a border in causality. Outside it, light can still escape if it is aimed correctly. Inside it, every future path leads deeper inward. Einstein's general relativity gives us this picture. Gravity is not just a force pulling objects together. Gravity is the curvature of space-time. Mass tells space-time how to curve, and curved space-time tells matter and light how to move. Near Earth, that curvature is small. Near a black hole, it becomes extreme. Light still travels at light speed locally, but the road beneath it is no longer straight in the ordinary sense. Space itself has been shaped so severely that some paths curve back into the darkness. So if the black hole itself gives us no light, why do we see anything at all? Because the black hole is not alone. Around many black holes, gas and dust spiral inward. This material forms an accretion disk, a vast rotating river of matter. The gas is heated by friction, magnetic fields, and violent motion until it glows. It moves at enormous speed, sometimes a significant fraction of the speed of light. The black hole remains dark, but the matter around it becomes a lamp. That lamp is what allows us to see the shadow. Imagine a bright background behind a black object. The object blocks some of the light, leaving a dark shape. A black hole does something similar, but in a far stranger way. It does not simply block light like a ball blocks sunlight. It bends light. It captures light. It redirects light from behind, above, and below. The dark region we see is not just the event horizon itself. It is the black hole's shadow, enlarged and shaped by gravitational lensing. This is why the first image mattered. The dark center was not the event horizon drawn directly on the sky. It was a larger shadow created because light passing too close to the black hole was swallowed. Even light that did not head straight into the hole could be bent so strongly that it crossed the event horizon anyway. Einstein's theory predicted that gravity should curve light. The black hole image showed that prediction in the strongest gravity environment humanity had ever imaged. But to understand the picture, we need three invisible boundaries. The first is the event horizon, the point of no return. The second is the photon sphere, a region where light can orbit the black hole. The third is the inner region of the accretion disk, where matter can no longer maintain stable circular motion and begins its final plunge. These are not all the same thing. That is the mistake many people make. They look at the black center and assume they are seeing the exact edge of the black hole, but the image is more complicated. The black hole curves the paths of light before that light ever reaches us. What arrives at the telescope is not a simple snapshot. It is a map of bent light paths. The photon sphere is especially strange. At this region, light can travel around the black hole in a circular path, not because it has slowed down. Light still moves at light speed. But space-time is curved so intensely that a straight path through that curved geometry loops around the black hole. In theory, if you could stand there, which you could not, you might see the back of your own head, because light from behind you could circle the black hole and reach your eyes. But these light orbits are unstable. A tiny change sends the photon outward to escape or inward to be lost. The edge of the black hole's shadow is shaped by those near-miss paths. Light rays that graze the region near the photon sphere and barely escape to our telescopes. That is why the shadow appears larger than the event horizon. The darkness in the image is not just the physical size of the horizon, it is the region of the sky from which light cannot reach us because gravity has captured those paths. Part 2. Now imagine the accretion disk. If we looked at it from above, it might seem like a glowing ring circling a dark center, but we almost never get such a perfect view in the universe. We see black holes from random angles. The disk may be tilted, it may be turbulent, it may be thick, uneven, and magnetically violent. Under normal conditions, if a disk were edge-on, we might expect the far side to be hidden behind the black hole. But near a black hole, hidden loses its ordinary meaning. Light from the back of the disk can bend over the top of the black hole and reach us. Light from the bottom of the disk can curve underneath and arrive at our telescopes. The black hole lets us see parts of the disk that should be behind it, because space-time redirects their light around the darkness. This is why black hole images can look so unnatural. You are not seeing an object lit from one side. You are seeing several gravitationally bent versions of the same surrounding material layered around a shadow. Some light reaches us directly. Some light loops around the black hole before escaping. Some light circles almost completely before finally leaving. Near the edge of the shadow, there can be increasingly thin rings of light, each produced by photons that made additional partial loops around the black hole. It is as if the black hole writes the same scene again and again around its own shadow. Einstein would have called this geometry, but to human eyes, it looks like a cosmic illusion. Then comes another effect. Brightness. The glowing ring is not evenly bright. One side often looks stronger than the other. This is not random decoration. The gas in the accretion disk is moving extremely fast. When the glowing matter moves toward us, its light is boosted. When it moves away, its light is weakened. This is called relativistic beaming or Doppler beaming. So the brighter side of the image tells us something about motion. It is not just where more matter exists. It is where motion, light, and relativity combine to amplify what we see. This is why a blurry ring can contain so much information. It can tell scientists about the black hole's mass. It can test whether the shadow has the size and shape predicted by general relativity. It can reveal how matter behaves near the edge of no return. It can show whether Einstein's theory still works, where gravity is at its most extreme. And this is why the first black hole image was not disappointing. It was not merely a photograph, it was a measurement of space-time. The Event Horizon Telescope achieved this by turning Earth itself into a telescope. Radio observatories across the planet observed the same target together. Their signals were combined using a technique called very long baseline interferometry. The farther apart the telescopes, the sharper the resolution. By linking telescopes across continents, scientists created a virtual telescope almost the size of Earth. Even then, the task was brutally difficult. The black hole in M87 is enormous, billions of times the mass of the Sun, but it is also tens of millions of light years away. From Earth, its shadow appears incredibly tiny. Imaging it was like trying to read a date on a coin from across a planet. Think about how impossible this achievement sounds. The shadow of M87's black hole is huge in reality, wider than our solar system. Yet from Earth it covers a tiny patch of sky. No single telescope could simply zoom in and photograph it like a planet. The Event Horizon Telescope had to collect radio waves from different locations on Earth, then compare the timing of those waves with extraordinary precision. The final picture was not a casual snapshot. It was reconstructed from patterns hidden inside enormous amounts of data. That is why the image looks soft. The blur is not weakness. It is the limit of trying to image one of the smallest looking and most extreme targets in the observable universe. The miracle is not that the picture lacked sharp detail. The miracle is that the shadow appeared at all. Yet the image appeared, a dark center, a bright crescent, a ring of light bent by gravity. The first target was not Sagittarius A star, the black hole in our own Milky Way. The first image released was the black hole in the galaxy M87. Sagittarius A star was imaged later. That matters because older explanations made before the release often expected our galactic center to be the first famous image. History turned out differently. M87's black hole was a better first target in one crucial way. It is much larger, so the glowing gas changes more slowly from our point of view. Sagittarius A star is much smaller, and its surrounding matter changes rapidly during observation, making the image harder to reconstruct. It is closer, but more restless. This is another lesson of black holes. Closer is not always easier, but both images told the same deep story. At the center of each was not a normal object, but a shadow caused by the capture of light. Around each was emission from matter moving in curved space-time. And behind each image was Einstein's claim that gravity is geometry. Now ask the most important question. What exactly did humanity see? We did not see the singularity. That remains hidden forever behind the horizon. We did not see a solid surface. Black holes do not have one in the ordinary sense. We did not even see the event horizon as a visible ring. Instead, we saw the shadow that the event horizon and curved light paths create against glowing matter. We saw absence made visible. We saw the place where outgoing futures end, outlined by matter still fighting outside. That is the beauty of the image. The black center is not a thing shining. It is a missing signal. It is the silence of light. And the ring around it is not just decoration. It is the universe screaming around a place where screams cannot return. Part 3. For Einstein, this would have been both triumph and mystery. His equations predicted a universe far stranger than the one our senses evolved to understand. He showed that time can slow, light can bend, and space can curve. But black holes pushed those ideas to their extreme. They suggested that space-time could fold into a region sealed from the rest of reality. Einstein himself was cautious about whether such objects truly existed in nature. But the universe did not need human comfort. Massive stars collapsed. Galaxies grew around compact, dark centers. Black holes merged and sent gravitational waves across the cosmos. And eventually, the Event Horizon Telescope gave us an image. That image was not sharp like a photograph from a phone. It could not be. The target was too far away, too small in the sky, and too strange. But its blur was not failure. It was the first direct horizon-scale evidence of a black hole's shadow. And what made it powerful was not the beauty of the ring alone. It was the agreement between observation and theory. The size of the shadow matched what general relativity expected for a black hole of that mass. The crescent shape made sense with fast-moving plasma and relativistic beaming. The darkness in the center matched the idea that light falling too close cannot escape. In other words, the image was not only showing us a black hole, it was asking Einstein's theory a question. Does gravity still behave as geometry when it becomes this extreme? So far, the answer appears to be yes. But black holes are not the end of questioning. They are the beginning of deeper questions. What happens to information that falls in? What replaces the singularity when quantum physics becomes important? Are the thin rings near the shadow edge hiding even more precise tests of gravity? Can future telescopes make movies of matter orbiting near the horizon? A black hole image is not a final answer. It is the first frame of a much longer investigation. The more clearly we see the ring, the more directly we test the edge of known physics. Better images may reveal changing hotspots in the accretion flow. They may show plasma moving around the black hole. They may help measure spin. They may show whether the shadow remains stable exactly as Einstein predicts. The first image looked like a blurry orange ring, but inside that blur was one of the most important messages humanity has ever received from space. It told us that a black hole is not just a mathematical monster. It told us that space-time really can curve into a trap. It told us that light can be bent, delayed, boosted, swallowed, and transformed into a visible shadow. And it told us that even when the universe hides something forever, it may still leave an outline. That outline is what we saw, not the black hole itself in the ordinary sense, not the singularity, not a surface, but the shadow of a place where light loses every road home. What feels more impossible to you? That humanity photographed a darkness 55 million light years away, or that this darkness was predicted by equations written more than a century ago? Subscribe to explore more documentaries through Einstein's questions, the questions that still lead us to the edge of reality.